Wait, this is a zero.
Leslie, can you just show me what proper?
No, I just went to the, so I can write on here, so I can reference. I don't have this one in zero. All right, which one?
Hello and welcome back.
I'm sorry. Shut up, I can't hear the question. No, that would just be an asymptote and then a defined point, yeah. No. What classify as in what do you mean? Yes, that matters. F. For this one, I would probably say the limit as x approaches c, and I wouldn't do one-sided. I would just say the limit overall, because one-sided they do equal. Or you could say does not equal, because at 0, I've got this point here, but what else?
We need to move on from this.
This was the easy part. All right, section 2. Find the values of x where the function is discontinuous. Classify each discontinuity. So if I'm not piecewise, then there's only 2 things that I'm looking. Now, piecewise would give me my jumps, right, and possibly my whole. If I'm not a piecewise, then I'm looking for asymptotes and wholes, right? Both occurring when denominators equal 0. So as I look at the first one, are there any of those? Yeah, but what kind of asymptotes are they? On the first one? Oh, I'm sorry. Are they wholes or asymptotes? How do you know? They're not canceling, they're asymptotes. So if they're asymptotes, it says find the values where it's discontinuous. So x equals 5, x equals -5, and all I have to do is say if it's removable or non-removable. Up top.
No, I like it this way. Don't change it. Don't change it.
Because if it has a vertical asymptote, it's not continuous. All right. D. I feel like I need to talk about D for just a second, so stay with me.
It's supposed to be a whole, but it's at A.
You did DC? Oh. Dang it. Okay. Well, let me just tell you something about D real quick while I'm right here and write this down. If you ever have an absolute value, the absolute value of x plus 3, you have to evaluate that 2 different ways. You have to evaluate it as x plus 3, and then you also have to evaluate it as, remember what absolute value does. It takes anything negative and makes it positive. Close, but it's actually going to be negative x minus 3. You change all the signs inside. And you'd look at it as, that's why it's whenever you graph an absolute value, it's 2 different things that are graphed. That's why, because you have to do the negative and the positive, yeah. Yeah.
I mean, if you value show up, but you're going to have the 0.
You're going to be fine. It's going to be fine. You're going to be fine. Just lock in. You're going to be fine. All right. C. I am going to factor out an x. I've got x equals 0 is a whole, so that's a removable. But x equals 1 is a vertical asymptote, so that's non-removable.
I did not write that in the whole.
It's a whole. You do, but if you have Algebra 2 was doing this yesterday. If you set this to 0 and you solve, right? This can go to 0, or this can go to 0. A zero product property.
So what you're saying is algebra 2
Because it cancels out. Because it cancels with that x in the top. Just like when the factors cancel out, because that cancels out. All right, F. F, you have to know what this looks like, right? And understand that tangent is the same thing, and this will come up a little bit in what we talk about today. Tangent is sine over cosine. So everywhere cosine is 0, I've got a vertical asymptote.
pi over 2 and 3 pi over 4.
So where is cosine 0? Cosine is my x. So at x equals pi over 2, right? Up at the top, x is 0. If I loop back around down at the bottom, 3 pi over 2, and I could continue this way. Those are all my vertical asymptotes. So those are non-removable. Not at a pi, because at a pi tangent is 0, not undefined. It would carry on in that form. It would be, you're saying, could you say plus pi? You could say pi over 2 plus k pi, where k is an integer. But no. This part though. Guys, this is why we're not getting through anything. Let everybody ask their questions. Be respectful. Yeah. Sometimes they'll ask you, describe the discontinuity as removable or non-removable. So you'll have to know. But asymptotes are always non-removable. The only thing that's removable are holes. Everything else. All right. No, I already said that. I know, because you were talking. All right, A and C, is that what y'all had? It's on the next page. State whether the function is continuous, and so what we're doing is we're testing those continuity points, right? So essentially all we're doing is plugging in the left. This side is the limit as x. I don't know why my pen is dragging now. As x approaches 2 from the left. Nope, that one's from the right. The first, that was right. Where's undo? That's a minus. And this one is from the right. Right? So all I'm doing is plugging into each one of those. 8 minus 2 squared, it's a big question, does that equal 6 minus 2? So it's continuous. And it's included here, so yes, it's continuous. Well, it says state the 3 criteria. That's just your limit as x approaches 2 from the left of f of x equals the limit as x approaches 2 from the right of f of x, which equals f of x. F of c, sorry. F of 2. Same thing with C. The first one's from the left, the second one's from the right. So the big question is 2 to the third the same thing as 10 minus 3? No. So it's not continuous. Is it a hole or a jump or an asymptote? It's a jump, right? Removable or non-removable? Non-removable discontinuity. It's a jump at 3. That's only when your bottom equals 0. There's no fraction, so there's no vertical asymptote. How you identify what? If something cancels top and bottom, that creates a hole. or on a piecewise like this, if that wasn't there, it would be a hole. It would make, yeah. You're looking for fractions for that. Depends on what scenario you're in. Are you asking for the homework, or are you asking in general for like? I would say that's good. Yeah. Yeah. I would say the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. And that is justification enough on any FRQ that they're just checking. Can you tell the definition of continuity? Can we look at your work and know that you knew the definition of continuity and that's what you just proved? Did you say 3? Oh, sorry. All right, part E. So part E looks like the possibility of a hole, but maybe that hole is plugged. You see what I'm saying? With the 3. So the question is, if I plug it, this is my limit as x approaches 2 from the, come on, left. This one is as x approaches 2 from the right. So if these two equal each other and they also equal 3, then I'm continuous. But if they don't equal 3, I'm not continuous. Do y'all understand? This is creating a hole or an asymptote or something of the sort. So let's see what happens. The top one is an asymptote. So what am I approaching as I approach 2 from the left? Positive infinity or negative infinity? Are you sure? How do you know? We're actually going to talk about this today. If this is not a calculator, how could you know? Well, as I approach 2 from the left, so if I plug values in really, really close to 2, but I'm approaching from the left, so less than 2. So something like 1.9. Am I getting a positive number or a negative number? Negative. So what am I approaching here? Negative. Right. If you think about your parent function, I've just slid to the right too. All right, and so the limit as I approach 2 from the right would be 3. They definitely don't equal, so there's no point in me even checking anything else because these are not the same, so it's not continuous. Does that make sense? Yeah, you'd probably just get one answer point, and that's it. You'd miss your other 2 or 3 points. Because it's an FRQ. You'd probably only get 1 point for the answer, but you'd miss all them. She said if you just put not continuous. There, and sometimes it's a 2-point question, and they just say, is it continuous? Justify your answer, and you've got to have the justification to get any points. All right, picking up the pace here just a little bit. How about 1.3, removing discontinuities? A and C is what you had. So again, I'm plugging in. So if this is continuous, then 2 squared better equal A minus 2, right? What do I need to use for A to make that happen? That's all you do. C is not as easy because there's 2 unknowns here. Again, if I plug in -1, so I got negative A plus 5, and it better equal A. If I plug in, is that right? No?
I want to know how to do some homework. I wouldn't do it right.
Oh, what the?
I kind of missed that part.
Yesterday, all I did was plug in -1 for the x's. I'm making it continuous. What they're saying is it may or may not be continuous here. What do I need to force continuity? If it were continuous, what value would need to be there? Okay, what did you do up here to check continuity? Look at part C. What did you do to see if you just plugged them in, right? And they had to do what for it to be continuous? Equal. So here, same thing. I just plugged it in and set them equal, right? For the x. Yeah, squared. This is a times -1 squared. So then I just added a to both sides. Yeah.
Two and a half.
Leave him alone.
Oh, I did too. I'm sure. I had it scanned too.
I didn't know we were switching.
I'll give you a little grace
Bye
today.
for Noah.
All right.
I honestly don't like the scanning.
Right now.
God.
Shut up!
Miguel, don't yell. All right, I think that was it. Was that it? Or did I? No, 5A. 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 All right. This is when it gets hard because I got two unknowns, right? So find an equation relating A and B if it's continuous at 1. Same thing. If it's continuous at 1, that means if I plug in 1 for x, it better equal, right? So b minus 1 better equal a times 1 minus 2 squared. Do y'all see where this is coming from? So b minus 1 better equal just a. It says an equation relating the two. That is an equation that relates the two.
You just had to set up.
1 minus 2 is -1 squared is 1. It's times. For which one? 6? Find the values for A and B. So this is what we were doing yesterday. That we're actually forcing it to be continuous. And I'm coming in from there's 2 places. Does everybody see that there's 2 places of possible discontinuity? At -2, that's the first possible place. And then at 1, there's the other possible place. So, same thing. If I plug in -2, -2 to the third plus 8 over -2 plus, oh, I can't do that. I gotta clean it up first. You see where my problem was here?
No way.
Oh, because it's going to cancel out.
It's gonna cancel out. That's right. Who do you think?
Ian Grayson, my little kitty.
Yeah. That was not.
All right. This is the difference of 2 cubes. Oh, I can't write right there. Apparently, I can't write anywhere. That is the first function if I take the hole out. If I remove the hole that's right there. Okay. But I'm going to fill in the 2. That's exactly right. So I'm going to evaluate when x equals -2. So I get 4 plus 4 plus 4, which is 12. Everybody okay? So this is my left side limit. I need my left limit to equal my right limit. Where is my right limit coming from? The second equation. So 2a, I need to plug in a negative 2 for x plus b. Better equal what? 12.
Okay, that's the setup.
Okay, so here's equation number 1 set up. Now what is equation number 2 set up? Well, I'm going to do the same thing, but I'm plugging in 1 to the second one, that's my left-hand limit, and 1 to the third one, that's my right-hand limit. And this time we're filling in 1 for x. That's exactly right. So I got 2a plus b, and that better equal, that's right. And all I asked you to do was set up these two equations. Why is it what? Yeah, I plugged in 1. I plugged in 1 for the x's. So I'm plugging in 1 for the x's here. That's my left-hand limit. 1 for the x's here. That's my right-hand limit. It depends on what they're asking you. Solving it like, well, these won't solve this way. In order to solve them, I'm going to have to set up a system of equations. But this, whenever I plugged in negative 2, there's no a or b in here. So when I plugged in negative 2, I just got a value. Right. If you were to solve it, and I didn't have you solve this because I didn't want you to get too bogged down, but this would be a plus 2b equals negative 2. And so I've got these two systems of equations. I'm with Logan. I'd probably do substitution on this one. This one's easy to get a by itself, or this one's easy to get b by itself. Where is what coming from? This is my left limit. This is my... Right. This is my... You're saying if I'm forcing it to be continuous, what do those... I am. So it says if you do force it to be continuous, what does that value need to be? Yeah. No, you would find a, but I told you just to set it up and leave it because it's coming into a system. But when you solve a system, remember, you solve for one of the variables, then I'd plug this back. This is where we got bogged down yesterday, and I felt really bad going into all that. But it's just like that one yesterday, and then we plug in. All right, for the sake of time, let's go on to number 7. I don't ever work every single one of y'all's homework problems, but clearly y'all had some issues.
Maybe you had something too.
Ooh, got you there.
What do you mean we didn't get to the homework? Yeah, we did. That was the last one we did. All right, how about 7? Which one? All right, so it has a value of f of 2. You do, and you make it fit this criteria. Everybody's can be different. A limit is x approaches 2, but it's not continuous at 2. So a whole, or what, at 2, it has a value at f of 2, so it can't be an infinity thing, right? It has a limit as it approaches 2. It says that x equals 2. It doesn't matter where it is.
I did it at 2 too, just to be safe. Or,
that's fine. Or you could have done maybe something like this where you did a jump. That would also fit the criteria. It's just got to be non-continuous.
No, but we're gonna have a limit.
Oh, you are right. You are right. So yeah, that's up to this. It has to have a limit. So it have to be the first. It have to be a whole. Mm-hmm. Because it says it has a value of f of 2. That's my point. This does have a limit as it approaches, but it's not continuous. It doesn't matter where it is on y. It only matters where it is on x. It has to approach 2. I could have put this anywhere. Which other one did I say, C? The limit as x approaches 4 of f of x equals negative 2, but the function is not continuous at x equals 4. Is the limit as x approaches 4 negative 2? Yep. Is it continuous at x equals 4? No. All right. Infinity and evaluating whenever we don't have a graph, whenever we do have a graph, and how we can. This was one thing that, and y'all can tell him I gave him a shout out if y'all are crazy. Robert Jenkins loves these. I don't know how he could see it, and none of the rest of us could always see, but this is very conceptual for some reason. The plugging in infinity. You have to treat it like a number, but then again, not like a number. So you'll see what I'm talking about.
Whoa, we're hitting 30.
Huh? All right, ready?
I have curves with all the right places.
Logan.
All right. Anybody knows what's that? That's what's cool.
You're a fed. You're a federal. That's what my Algebra 1 kid said yesterday. You're a federal. No. I'm gonna try to make this as easy as possible. All right. Remember, this whole unit is about limits, and we're only going to how many are on that unit 1 list? 18, 16. It should be numbered. 16. So this is 14. Okay, 14 and 15 today. 14 and 15. All right, we are getting close to the end, but we'll pull it all together. All right, so this is, we're not, yeah, but they make it longer than what it has to be. 15 is really where the meat of the stuff is, though, that I want to talk about. I'm just going to brush over this on what we need to do. All right, here's what you need to know. Limits as that are going to infinity. If you ever take the limit as x approaches some value, either from the left or from the right, this is one of those things that just makes sense, but they might say, why does this happen? If you ever get positive or negative infinity, that is the definition of a vertical asymptote. Period. If you take the limit as you approach a constant value and you get infinity, either positive or negative, you have a vertical asymptote. That's what it means. There is a box at the bottom of your paper that even has this highlighted down there if you'd rather not write it or if you want to write it. That's your huge takeaway here. I am not going to go over all examples 2 and 3 where they have you find the vertical asymptotes. We have been drilling that. When do you have a vertical asymptote? Algebraically. When the bottom doesn't cancel out, it equals 0, There's no whole, I'm looking for fractions, that's exactly right. So if you just glance over at examples 2 and 3, that's what we did with our discontinuities yesterday. That's what we've been talking about in pre-cal. If you need some extra practice with that, you can look at those. What I do want to go to is down to example 4 for just a second, because, and we kind of talked about this just a minute ago. I think Logan was the one that got the infinity wrong here. But if I want to know which way my graph is going, right? So maybe I don't have a calculator on this, and I want to know the limit. I know there's a vertical asymptote, right? We all agree that there's a vertical asymptote where here? At 1. But the question is, which way is my graph going? Because this is saying as x approaches 1 from the left, right? So from the left, and this is an easy example, but just to show you, as I approach from the left, that means I'm looking at numbers like 0.9, 0.99, 0.9999. Can we what? So the question is, all I really need to know, because I know it's a vertical asymptote, so I know the limit as I approach is either going to be, plus or negative infinity. I just have to decide which one. So if I plug in any of these values, am I going to get a positive or a negative number? Negative. Because 0.9 minus 1 gives me negative. So this would be going to negative infinity. It's that easy. Yep, from the right. So if I plug in a number that approaches 1 from the right, so a little bit bigger than 1, maybe 1.1, I get positive, so this has got to be positive. So if I'm from the right, think about a number line, right? Here's 1. If I'm approaching from this way, so maybe I plug in like 1.1 or 1.01, but whenever I do that here, am I getting a positive or a negative number? Positive, so it's positive infinity. Easy enough? So maybe you have the question, how do you know that there's a vertical asymptote? I know there's a vertical asymptote because as I approach 1 to the right, the limit is negative infinity. That is the definition of a vertical asymptote. That's the most you need to know with it. Everybody okay? That's all of 14. That's why I said I was rolling 15 in with it.
Homework.
No, it should be, woo, we got 40 minutes. Yeah, we will. We'll have homework time. Y'all also have me do your entire homework from yesterday. All right.
Ooh, he got you there.
Now, vertical asymptotes, as I approach a constant, I get infinity. Vertical asymptotes are a little bit different, and I'm kind of skipping around in this section, so I'm really sorry that I am. I'm going all the way back, and then I'm going to come back to how we evaluate algebraically. But horizontal asymptotes, if I ever approach positive or negative infinity, and I get a number, that is the definition of a horizontal asymptote. Think about what that looks like on a graph. What's the limit as x approaches infinity? 1, because it's getting closer. That's a horizontal asymptote. That's the definition of a horizontal asymptote. Everybody okay? Yep. So if I approach a constant and I get infinity, I'm a vertical asymptote. But if I approach infinity and get a constant, while I'm right here, tell me algebraically how I can see or tell if there's a horizontal asymptote? If it's a rational function. Top heavy's none. Bottom heavy, 0.
And then if they're the same, you divide the leading coefficient.
If they're equal, then it's the leading coefficient.
And we're talking about the leading coefficient.
Right. We're talking about the degrees. Y'all want me to write those? Top heavy. These are for horizontal asymptotes. Rational. What's a rational function? Fraction. Right. Top heavy, meaning the degree of the top is bigger than the degree of the bottom. No horizontal asymptote. Did you see that curve? Bottom heavy. And same leading coefficient of the top divided by leading coefficient of the bottom. Yes, it's a fraction, yeah. Yeah.
Oh, I get why.
All right, let's do the fun stuff. What's what? Probably a crap ton. All right, let me talk just a minute about evaluating algebraically. Ugh. Turn around, Logan. Me?
Oh, yeah.
I'm looking. I'm trying to. Oh. Look at example 6 at the bottom. Yours is mine flips over. The bottom page 22. Say again? Well, no, so what you have to do whenever you evaluate these, okay, is we're going to plug in infinity, but we're going to think about infinity conceptually. So, like, look at example 6. I've got the limit as x approaches infinity of 5 minus 2 over x squared. Now, I could go through this. I could make it into one single fraction, and I could go through, try to find make the rational function, but I'm not going to do that. Instead, what I'm going to do is I'm going to plug in. You know how we always try to plug in for limits whenever it's going to a value, and then sometimes we can't, so we have to manipulate it. I'm going to do the same thing, but with an infinity. And I want you to think about this for just a second. If I plug in, I've got 5 minus 2 over infinity squared. Right? Okay, but think about this. You've got 2 over infinity squared. What happens if you take the 5, the 2's not really impacting it, but what happens if you divide something by a really, really big number? Like if you have a number divided by a huge, you get a real, and what happens as that number gets bigger and bigger and bigger on the bottom? Number gets smaller and smaller and smaller. Remember, we're thinking limit-wise, so it's getting closer and closer to what? 0. So I'm going to say this is going to 0. And in fact, anytime you have a number over infinity, not a variable, but just a number over infinity, that is always going to 0. This is going to 0 pretty fast because it's infinity squared, right? So if that goes to 0, then what do you think this limit is? And it is. So we're using infinity to plug in, but we're really having to kind of think about it. You say it's not bad right now. Some people see this and they go, oh my gosh, why did you even say that? But then other people go, this is ridiculously hard. Look at 7. Let's plug in infinity. Are we going negative or positive? Positive. So the limit is x goes to infinity, 2x minus 1 over x plus 1. So let's plug our infinity in. Now, if you're dealing in infinity, okay, we know by our rational functions what should be the asymptote here. Horizontal, 2. Somebody said 2. Y 2. Same degree, right? Y equals 2. I'm going to infinity. That's by definition a horizontal. So what I'm looking for whenever I take it to infinity and negative infinity is I'm looking for horizontal asymptotes. Okay? I should get 2, but let's plug it in and see. If I have infinity and I subtract 1, does that make a difference? It's not going to make much difference at all. I'm going to just eliminate those. Because remember, I'm thinking about this conceptually. Adding 1 or subtracting 1 from infinity is not doing anything. Now, I think this is why I don't like this. Huh? Then you're just left with the double. The infinities cancel. Because if you add or subtract anything to infinity, it's never going to matter. If you have a number off to the end, you don't even have to worry about them. Okay? It's still going to be infinite. That's exactly right. Let's do.
Yeah.
No, because 8's the same way. It's pretty easy. I want to jump down to 9.
Hold on. For A, you just
Y'all go fuss about this homework thing.
for A, you just know.
A right quick. All right, 2 times infinity plus 5 over 3 times infinity squared plus 1. Now I know it's bottom heavy. I better get what? 0. All right, these are not impacting whatsoever, right? I've got 1 infinity up top. I've got 2 infinities in the bottom, so I'll take 1 out. And now I've got 2 over 3 times infinity. I'm getting really, really huge in the bottom. No, I mean in this case it doesn't. Watch this one. Do B? Because a number times, yeah, if infinity's in the bottom and there's no infinity in the top or anything, it's going to 0 every time. Your infinities are going to cancel out here and just give you 2/3. Look at example 9. Try part A. And if I plug in here,
Hold on, what?
Adding to infinity is useless on this addition.
all that addition and subtraction is useless because it's going to Remember your properties of radicals? I can split that up, right? Let me get out of here. So what happens here when I do the square root of something squared? It cancels. So now that's okay. Let me just write this now. Slow down. Dozier, did you get this one? Close. Well, you don't have to rationalize down calculus. You can leave it on that. I thought you said 3 over 2. The infinities can cancel. If you want 3 root 2 over 2.
So you spent 2 years telling us to get rid of radicals.
Get rid of the radical in the bottom.
And now we can leave it because we're in calculus.
Do B and see what you get. See how it's different. No. Yo, Wyatt. Right.
No, negative. And you stop.
So this tells me I have horizontal asymptotes here, as well on each side. All right, before I set you loose, I do want to flip over to those last 2 multiple choice multiplication problems. Flip over to page 25.
Can we get a multiplication site? Whoa! Whoa! Whoa!
I can handle that when I get home.
Ooh, she said with the belt. Stop. Hey, Doja, you going to Slapbox today after school? Miss McGee said it was good. You remember that before she was recording at the start of class?
Well, I don't know what that is.
That would be awesome.
Oh, you're going to be an Olympic gold medalist.
All right, I would be remiss if I did not show you how this was applied on the exam. Stay with me. I just have a little bit longer. Just these 2 quickly. This is a 2012 multiple choice question that showed up. The line y equals 5 is a horizontal asymptote to which of the following function? So this is a non-calculator. And maybe you do know stuff about rational functions and you remember it, or maybe you don't, right? But how can I tell which one has a horizontal asymptote at 5? I'm looking for one that the limit as I approach either positive or negative infinity is going to give me 5. So if I plug in an infinity or a negative infinity, first of all, what happens if I plug in, we didn't talk about a trig function, but what happens here if I plug in infinity? 0. Good job, y'all, because the top's always going to fluctuate between -1 and 1. The bottom's going to 0, so it's going to be 0 every time. So it can't be that one. I said if you know, right. If you remember your rules from pre-cal, this makes it, a lot of these problems you'll see you can do with algebra and pre-cal, and you don't even have to apply the cal. This is the calculus. This is the calculus way. This is the pre-cal way of saying 20 divided by 4 is 5 since they have equal degrees. But there you go, it's E. That'd be -5. Come at that one. D would be -5. And then on the next one, this was in 2008. This one a little bit harder, right? What are all the horizontal asymptotes of the graph? So this one is going to require me to go in and say, okay, now I do need to use the calculus, right? This is not a rational function. So what's the limit as x approaches infinity? And then what's the limit as x approaches negative infinity? And that's going to, because by definition, that's what a horizontal asymptote is. So if you kind of plug in there, if you plug in there, it was mean. All right, so what happens here if I plug in infinity? This is your time to shine.
Oh, yes, you can. Ain't calculus.
What happens here? Close. -1. Because this is a -2 on the bottom here. Because, all right, so these don't really matter, right? 2 to the infinity is really, really, really big, right? Divided by a negative really, 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 really big. So really big divided by negative really big. Same thing on the other way. Yep. So now as I go negative infinity, I'm just going to ignore these right now. I know they're not going to do anything. 2 to the negative infinity over -2. Remember what negative exponents do, which doesn't really matter in this case. Wait. We can't cancel these. We can't cancel these this 5 and this 1 this time. Let me show you why we can't. Whenever it's negative infinity, if I've got 5 plus 2 to the negative infinity over 1 minus 2 to the negative infinity, this is not just really huge anymore. What is it? Really small. So this is 0. And this is 0. I can't cross this out. Initially, I can't cross this out. Oh, that is. So, yes.